It's always a pleasure to come to Loyola. Though I did not have the opportunity to study in Loyola because I didn't have enough marks in my PU and BSc, I always knew we had very close interactions with some of my classmates who came to Loyola because I was in a precursor. I did my schooling in a precursor institute to Loyola, which was Don Bosco at Egmore. So today I was thinking of doing something that is building a culture of research in higher education institutions. This is a very personal perspective, and it will be leaning towards chemistry, and those are only examples. So if you have any doubts, I will try my best to address those doubts. You can, any comments that you want, which for paucity of time we are not able to discuss, you can send me an email. Just in your subject line, you can see where we met. And if you want to know more about our work, we do a lot of fun things, which I will try to tell you here. And if you want to really see how we did all those fun things, you can look at our site here. So before we start, what is research in higher education, if you look at it? In 2003, there was a university in China, in Shanghai, which started this thing called Academic Ranking of World Universities. So you can just put in Google search, it's called ARWU. And this thing is www.shanghai-rating.com. Of course, now you will see that you have a lot of the QS rankings, the Times Higher Education rankings, but this remains for me the most important ranking as far as research is concerned. It gives a lot of accent to research and also to teaching, but mostly to research and how students who left that particular university actually perceive that university, which is very, very important. So this particular thing has been there for 16 years. And then if you go into their website, onto your right of the screen, you will see that they have a very nice 20-page booklet in PDF format, which is saying Discovering World Class. What we use this word so freely, without understanding anything. I will show you what world class means when we compare some of the universities, the top universities in Asia, to maybe the Indian Institute of Science, which is the top institute in India. I would like all of you to just go whenever you have the time to actually go to this. Maybe another thing that I would like all of you to look at is maybe the greatest educationist of our times. His name was Clark Kerr, and he was the president of the University of California's Berkeley, and it was called Berkeley College. And once the World War was over, it was said, the president at that time in the United States said, that a lot of army people, young guys who will be coming in, you have to give them holistic education. So he thought about this and said, let us start this University of California systems. So you will see that there are now 8 universities of the University of California, Berkeley, Los Angeles, Riverside, etc., etc. The latest one being Merced, which is in Northern California. And this is his most famous saying was this, that we have to make students safe for ideas, not ideas safe for students. I think this is what the whole research is all about. And the other thing that he said, a university anywhere can aim no higher than to be as British as possible for the sake of undergraduates, as German as possible for the sake of public at large, and as confused as possible for the preservation of the whole uneasy balance. So this gives us a rather good run up to this, because we actually have only follow the British system. So the way that we treat our undergraduates, etc., is actually world class. Of course, German, this thing of social, this thing, luckily we are a socialist country, and therefore this kind of a social behavior is actually ingrained into our brain. So the idea is that not to compartmentalize these two, but to see whether we can get both of them together and actually make something very, very good for this country. He also wrote a fantastic book called The Uses of the University. It is actually freely available now on the web. And also two books. It's called The Gold and the Blue. The volume one is a personal memoir of the University of California. How do you choose to be world class at that time in 1957? How do you choose your faculty? How do you choose your students? What do they give them, etc., etc.? Again, a very nice free book on this is available. What is most important is that the University of California at Berkeley instituted what are known as the Clark Kerr lectures, which I have given in the last the website. I would like all of you to go through this. I mean, there are about 25 of them now. Every 2 years they have this Clark lectures, and they are from a very this thing of how industry should help the university to now the MOOCs revolution. So you can see that all this is put into this. It's worth reading when you have listening, because each lecture is about 1.5 hours in duration. So as we go as a country, the questions that we have to ask is, can India afford bleeding edge research? So is reinventing the wheel in the current context a viable option? Does having a unique, does have an undergraduate and a postgraduate program inside a university? For example, you will see now the Indian Institute of Science. About 10 years ago, I started an undergraduate program, a BS-MS program. There are what are known as the Indian Institutes of Science, Education and Research. We supposedly trying to be as good as the Indian Institute of Science, but having a huge population of undergraduate students. And how do we put all these together and leverage this as an advantage for all of us? So this is something we will try to answer as we go on. So look at, for example, the budget of MIT. The ARWU 2018 rankings are out. MIT is the best university in the world, as usual. But look at their expenditure per year. It is about 3.34, the revenue is about $3.349 billion, which is about, now in this thing, about 21,000 crores per year is their revenue. 21,000 crores is their expenditure. For sponsored research, they spend $1.4 billion, which is about 11,000 crores. I mean, this is, to stand first, you need 11,000 crores. Okay, this is the thing. Of course, you can see 27% for instruction, unsponsored research, etc., 25% for general administrative, auxiliary, and the MIT alumni gives them about $17 million. You can also see how their revenue goes, research revenue. They also have the Singapore Alliance, etc. So this is exactly how this is. So can we even compete with them? I mean, if you now look at, this is the 2017 budget of the Indian Institute of Science, which is 1,000 crores. 1,000, this is in lakhs, so it's about 1,020 crores. This is our budget for the Indian Institute of Science. And again, you can see for research, everything is done here. And of course, their payments, etc., is 91,000 crores. So they get about 100 crores as some kind of a kitty that is there. But you will see that out of this, everything comes from the government. I mean, most of it comes from the payment, the salaries, studentship, everything comes from the government. While in MIT, it's of course not the case. For example, MIT would charge you $50,000 per year to do a course, 35 lakhs a year for the undergraduate course. IIT charges 2 lakhs. The outgo for one particular undergraduate student is 12 lakhs. So you and I subsidize the IIT students for about 10 lakhs from the kind of IT we pay, the kind of indirect taxes we pay actually subsidizes a student for about 10 lakhs. It subsidizes an IAAC or an ISA student for about 5 lakhs. So this is the whole idea. So now everybody is catching up. After ARWU rankings came in, you will see Tsinghua University in Beijing has a budget, annual budget of $3.3 billion. And now this year, it has more STEM papers, that is science, technology, engineering, and mathematics papers than any of the first 10 universities in the world. So by 2019, they will break into the first 10 universities in the world. NUS is already there. It's ranked about 12. It has, again, a budget of 3 billion. University of Tokyo is ranked about 20th, has a budget of 3 billion. And you can see all around us, you can see that everybody spends at least $3 billion, 20,000 crores for a year for becoming the best universities in the world. Indian Institute of Science, recently we would have heard in the paper, has got the Institute of Eminence, and that is a partly 200 crores per year for the next 5 years or so. So that will be about 1,000 crores. So with this, you will see that to do cutting edge research is becoming more and more impossible. If there are life scientists, you would see how do I defeat a genetic disease. You will see that you do what is known as molecular biology. But now it has advanced so much that you have what are known as CRISPR-Cas technologies. And to do one CRISPR-Cas experiment would take you about 10 lakhs, which is impossible in a setup unless there is some private donation into this. But we need translational research. Where are we in one sense that what are all the diseases that are there prevalent in India that the other parts of the world don't care? So can we leverage, go inside that, try to get a vaccine and a cure for a disease, and then try to get a more global feel of how these experiments have been done. So this is one thing. The second one is the low-cost instrumentation. Can we make instruments that are very low cost? Can we make, say, a microscope for 10,000 rupees, which can do a lot of things? And this, you will see, is possible. I'll give this as an example from my own lab as we go in. And what is known as frugal innovation. So frugal innovation is if you cut the cost of a product by about 80% with the same kind of things, that is the same kind of reliability, etc., you will see that involves frugal innovation. So the new age mantra, if you can call it, is that it should be interdisciplinary. It is rather unfortunate. I tell all my students that you have to be a jack of all trades but master of one. I mean, that's the new age mantra, that you should know everything. I mean, physics, chemistry, mathematics, biology, and then you must be very, very good in one subject, either chemistry, physics, math, or biology, so that you can interact with others and then make your work better and better as you go. You have to have collaborators. You really have to do deep research. Then you have to have collaborators who can understand the problem and actually give solutions to these problems. And of course, the preliminary work, etc., etc. So some of the areas of current research that we can really look forward to do is energy and materials. I mean, how can we harness this bountiful solar energy that is there? We are surrounded by oceans. Can we now use tidal power, at least in the coastal areas? The difference in temperature between the surface of the sea and the maybe about 100 feet below, the temperature difference is about 30-40 degrees. Can you actually run a huge refrigerator, etc.? The other one is food, nutrition, and health. India has babies, infants, whose levels of malnutrition are even worse than sub-Saharan Africa. Genetically, sometimes we are not able to take in micronutrients. For example, zinc. Zinc protects us from a lot of viral attacks when we are young, makes sure that foods get absorbed, etc. But unfortunately, we seem to have some genetic thing against this intake of food. And health. Somehow, if you look back, you will see that India was ravaged by famines, and therefore we have what is known as a thrifty gene. So what happens here is that we tend to store fat, and whenever there was a famine outbreak, we would use that fat and try to live. But now, unfortunately, that has gone against us, because food is available, and therefore once you eat, you become overweight, and therefore this leads to a lot of other diseases like diabetes, obesity, etc., etc. And then environment. Environment, in one sense, is related to both these two, and therefore I actually left it like this. So these are some of the areas that you can think of and come with viable solutions. And I think being in a small campus like this, it is actually much, much better that all of you can come together and work on some very, very nice topics. So for example, I do give this as an example. One is biofuel. You will see here that I think by the end of next year, it is mandated that 10% of our petrol should have ethanol. But ethanol has a problem. It is highly volatile. So can we have butanol? Butanol is less volatile, can be easily taken, can be stored without any major hazards of fire. So can you look at molecular biology for improvement of strains? Now you also saw that how Delhi is getting ravaged by this burning of these shoots that are there. And can there be a way by which we can take this, hydrolyze it chemically, and then biologically and actually produce ethanol. So these are some of the ideas one can think of and do this. The other one is food and nutrition. One great thing is clean water. So how do we remove microorganisms from water, heavy metals, arsenic, fluoride, etc., etc. I will again try to give you a very, very small example, some preliminary work that we are doing on this. Maybe you guys can also think about how to do this. So this again has an interdisciplinary favor. You need chemistry, environmental engineers, chemical engineers, and design engineers to make all this stuff happen. You can make everything happen in the lab at 250 ml, but what you need is kiloliters of clean water. So how do you do this? You have to have design engineers to do this. So micronutrients, most of it is zinc. Can it be easily delivered in an absorbable form? Again, you will see that here nanotech seems to play a part. Mostly you will see now that zinc is given as the zinc salt of glucaric acid, and but it is chunky. So can you now make it into a very nice formulation that can be nano and therefore can be easily absorbed? So this again has doctors, chemists, physicists, and technologists. And then materials, biomaterials, chemistry, doctors, engineers, and technology, because you will see that as we go on, plastics are going to be a thing of the past. How do we make biomaterials that can withstand a hot cup of tea, etc., etc. And materials so again you will see here chemistry, doctors, engineers, and technology. Materials for solar energy conversion, chemistry, physics, engineers, and technology. So not that now that India is not trying. I mean, that's one thing that I would like to. It's not as abysmal as I give. You can see some of these things that I have given. One is the research park at IIT Madras, which actually has about 1 million square feet of space. It is all given to entrepreneurs or even IIT students who want to incubate companies with a mentor from the Indian Institute of Science, from the IIT. I would like you to just go through that to see the kind of companies that are getting incubated. In contrast, I would also like you to see what is happening at the EPFL, which is at Switzerland. This is the Ecole Polytechnique. And you can see how they have done this, the number of companies that they incubate. Actually, one of our students who did his BTech went and did his PhD at EPFL and now runs a company out of this park. Of course, IAC has started one right now. And then there's something called the Research Triangle Park. This is between North Carolina State University, the University of North Carolina, and Duke University. It's in between these three universities. It's like a triangle. And you could see some of the things that they have incubated, some of the innovations that they have done. So just to give you an idea of what frugal innovation is, these are the three criteria that constitute frugal innovation. This particular, you can just go to the Google search, Journal of Frugal Innovation. This is freely available article. And you can see if there's a substantial cost reduction, you can call it frugal innovation. For example, from 100% to get it to 20%. So cost improvement by a few percent is not frugal innovation. So concentration on core functionalities. And you can see here that it has to run, it has to do whatever it was supposed to do. Optimized performance level. The performance level should be very good. What I tell you is in that triangle that is inside that polygon that is inside the bigger polygon, those are the core optimized functional levels, that you have to make sure that the optimized performance level is very good. So you have to compare it. Some of them can be missing, but in the whole, it should actually be viable. Has been done. Again, I would like you to go through this particular Indian site. This is at Gujarat, a company called mitticool.com. Here, during the Gujarat earthquake about 15 years ago, people lost their homes, their belongings, etc., etc. And this guy from Gujarat came up with this idea of making a refrigerator made of clay. And he actually made this clay. Is it frugal innovation? It looks as if it's frugal innovation because the cost of this is about 3,500 rupees. It keeps the temperature, it keeps the fruits inside at 8 degrees centigrade. It's okay. Then he has, so just you can go to his website. He has made a cooker made of clay, which you can cook rice in this. You can also have a nice dripping water container. You can order it online. You just saw it day before yesterday that you can order all this online. So this is something that is actually very, very good. Another great this thing was what was known as the Foldscope. This was actually done by an Indian who's a professor of bioengineering at University of California at San Diego. His name is Manu Prakash. And he has done what is known as, from a paper, using just cardboard, he has made what is known as a Foldscope. So this is, you can go, it's called foldscope.com. And you can enlarge anything 200 times. Okay, so you can actually see fungi, you can see cell walls, etc., etc. So this is now taken up by DBT, and DBT has, because this whole thing costs about 25 rupees or so, this whole thing. So DBT gives free this thing of this, or what they tell us that they have given 200 people, scientists, a project on this, 7 lakhs each. The idea is that we train people on this. So we were one of the recipients of this project. And so we are planning to have about a series of workshop in February. Maybe I will put Vincent's name so that I can send you that brochure. So this is something that we never know. We think that the solar radiation spectrum only is in the visible range because we see these green trees doing photosynthesis, and that's in the range where we can see, so which is between 500 nanometers to about 750 nanometers. So this is where we think that the solar energy is. But if you had looked very carefully, people would tell you that during a solar eclipse, never look at the sun directly. Do you know why? Do you know why? That it is nothing, it is very scientific. I mean, it's nothing, they always say don't look at the sun directly during a solar eclipse. I mean, especially total solar eclipse. Do you know why? Because of that, what we see there, from 1250 nanometers to 2500 nanometers. So this is in the IR region. So when we look at it, we can't see IR, but we can see visible. So when we look at the sun, we naturally crinkle our eyes. But when it is dark, we may just continue staring at it. But the IR radiation will come and then cook our eyes, basically. And that's exactly why they tell you never always use the welder's glass, because you will see the welder's glass, when they heat something, it's red hot, and that red is actually IR radiation. So we said, oh, this is a great idea. It's not too bad. So can we use this for some reactions? So this is where our work started. So what we did here was that for clean water, can we do something? So what we did was we took different glass bottles, put it on a silver sheet, and then when the ambient temperature, it was kept on a building at Center for Biotech at when the ambient temperature was 33 degrees. And then we started measuring it. And then when we measured it, we found out that the black bottle went 5 degrees above ambient to about 38 degrees. Then we said, oh, look, now if in Chennai, especially if you are in the final floor of your building, you are in big trouble during the summer months because it heats up like crazy, the last floor of a nice tall building. So what people now do is that they, instead of putting usual tiles, they put what are known as heat reflecting tiles. And so that is the heat reflecting tile. And that heat reflecting tile actually radiates IR very, very fast. So we said, okay, let's keep it on that tile and see what happens to the temperature. And we went up to about 47 degrees. So you just keep a bottle of water on a IR tile when your ambient temperature is about 35, it'll go to about 47 degrees. So now we are trying to see whether we can put a little bit of say bleaching powder and see whether that will decompose at 48 degrees and see whether we can use that for cleaning up water. So these are some of the things that we can actually do. So these are what I call some kind of frugal innovation. Of course, we have to make sure that both the chemistry and the science is correct, which I hope we will do at some point in time. The second one was what we found was that if you look at the absorption peak of nitric acid, it is about 3,000, it's about close to about 4,000 centimeters inverse 1, which is basically about 2,500 nanometers. And you see that the sun actually has a tail at 2,500 nanometers. So you just keep nitric acid there and on a sunny day, and you can see that it starts decomposing to NO2, and you get NO2 gas. So what we have done here is that you can see, maybe I'll use my hand. So you can see here that we have put a frit here, and we have kept a compound here. What we have done here is that we have, on the frit, we have put tyrosine, phenylalanine, all the aromatic amino acids, and see whether it gets nitrated. So we have just given that for mass spec. Why is this important? Because sometimes you can see that these compounds that get nitrated are very, very important in one sense, because most of these, if you take it in small doses, release NO, nitric oxide. And nitric oxide is what dilates your vessel. So when one has a heart attack or some heart failure, you're always given some nitro compound so that NO is formed. So of course, we had an idea that if this is really true, this is a gas-solid reaction. So can we now put, say, a bovine serum, any protein there, and see whether that gets nitrated, then do a mass spec, compare it with the native protein and this, and try to work out the sequence. I need some mathematics and statistics help, which is something that we do. The second one that we did was on seashells that are so abundant in our sea. So how do shells form? How does the mollusk know how to grow shells? The mollusk that lives inside the shell, how does it know that you should? So what it does is it's much cleverer than we thought. What it does is that once it's inside, it starts giving out proteins, right? And these proteins are fantastic because these proteins form, and then On that, the calcium carbonate actually crystallizes, and therefore you get layer by layer. I don't know. You have to use your imagination. You can actually see this, like this, striations, and that is actually where we think the protein is. What we have done in this experiment is to put the shell in a silver nitrate solution overnight, then washed it and passed H2S. So wherever the silver is, we think that's the silver has absorbed on that protein, and then this H2S has reacted with that silver, forming silver sulfide. Now, if you have a silver piece inside in your house, you will see that after some time it becomes black. That's because of the H2S that's there. And so we said, okay, that. So now the idea is that can we now use these kinds of proteins to crystallize proteins? It's very difficult to crystallize proteins. So I'm just talking to one of my friends who is a very good protein crystallographer to see how we can crystallize proteins using this. The other thing that we are also looking at is that I don't know, the other picture is very bad, but you will see some kind of a yellow band. So that is actually cadmium. So we have used cadmium sulfide, did that, and you can see so is it possible that these proteins can also be used to clean up metals? I mean, reclariant metals like cadmium, copper, etc., etc. The other thing is that if you can crush this into a very small particle, can you use this cadmium sulfide for solar energy conversion? Cadmium sulfide is known to split water, etc., etc., split dirt, and then actually make it into carbon dioxide and water. So these are some of the things that I thought I'll show you, because I'm going to retire in 8 months, and maybe you guys should actually carry on some kind of things like this. The last part, another 5 minutes? Great. Okay. So the other thing that I was thinking is, I was telling you that how can we make things, right? So this is something that we have to do. We have to make our students do. So this is a fluorescent workstation that 3 of my undergraduate students did. They were, in a typical sense, they were very bad students. Nobody took them for their final year project. But then that's because they were not interested in biotech. I mean, they said, we are interested in mechanical engineering, give us a design project. So I said, oh, let's then design this. Not that it was not known. So it was actually, so these guys went to Paris in North Chennai, and actually cut all this, did laser cutting and did all this. Then they got the Raspberry Pi. This is a great computer that comes in just like this. It's like the size of your cell phone. You can put it, it'll do all kinds of calculations for you. Then there is something called a Raspberry Pi camera, which is an 8MP camera, which can actually be connected to that, and then it'll take images of all the things that you do. And this was our LED that we put it at the base, and therefore you can see this. So this was a super bright LED at 470 nanometers, and we did this, and this is exactly how we worked. The idea here is that we are, as far as microscopy is concerned, especially using new technologies in science, we are all at the same level. I mean, you can get any of these things here that you can get in the US for maybe about 25% more. So the crux is the software. How do you design the software to look at these things? And that is something that we can do. Indians are great at doing actually writing programs, and they can actually do this. So you can see here, I hope you can see this. So this is a leaf inside a test tube, and you can see that this is fluorescing red, and this is perfect. And this is actually a gel picture that we have done here. Of course, now we have to write the program. The idea is that if you now take a plant, cut a little bit of the leaf from the plant, and can quantify the amount of chlorophyll, you can see whether that plant is in good health or not. And can you now give systematically something? Of course, the biggest plan would be to put this whole thing on a drone and send it across the field so that it can take all this. So the whole cost of this was about 10,000 rupees. So we built the whole thing for 10,000. Our cost pricing, we said we should get it to below 10,000, but it overshot it by about 150 rupees or so. So the next thing that we are trying to do is to build our own lenses. So again, I would like all of you to look at this particular paper, which is freely available. So you can see that these are some of what are known as polysiloxane lenses, which we use for our lenses that we have. But you can also see that we have made lenses. Those on the right is actually the lenses made in my lab. You can actually put those lenses on your smartphone and it becomes a magnifying glass. You can actually read it. I mean, we haven't gone further than that. The idea, the best would be to have this lens A here. So we are now on a glass. I had a student from ISA. So we were trying to make a nice hole in a glass, not a hole, a sort of a cavity, so that we can now put that, fill it with polydimethyl siloxane, put it on a beaker, and therefore see whether we can get nice spherical lenses like this. So these are some of the future work that we want to do, which I think all of us can do. I mean, it's not that we want to do, but all of us can do. Can we now, if you look at the foldscope, the light source is the light that is there. So can we now use 365 UV LED, ultraviolet LED, which costs about 25 rupees a piece, and then make it into a fluorescence microscope. And if you make it into a fluorescence microscope, you can peer a little deeper into your cell. So all these are some of the things that we are trying to do. Another thing that we are now at, you can actually buy, yesterday I was just looking at something, you can actually buy a 3D printer for about 39,000 rupees, which was the cost of a laser printer about 5 years ago. So with this 3D printer, you can print anything that you want, and then you can slowly start converting some of these equipment into low-cost, superior equipment. Why I am telling you all this is the starting point of getting into big things. For example, you would see that a lot of these AFM companies that started were actually students who said, let's build our own thing. I mean, it's so easy to build, and they started building. And then it became companies, they have sold it, become millionaires, etc., etc. Not too difficult to do. So I close this with a very nice saying from a famous ballerina, Margaret Fontaine, in her memoirs. She says, I cannot imagine feeling like a bicycle about a performance. I treat each encounter as a matter of life and death. So do it. That is the way you have to do this. The important thing that I've learned over the years is the difference between taking one's work seriously and oneself seriously. The first is imperative, the second disastrous. Thank you very much. Yeah.
Can you compare Mike?
Yes, sir.
Growth of ICT.
ICT. Oh, good.
Instead of biotechnology in India.
Okay. Excellent question. This is something that I should have touched, but I didn't. This is ICT with computer technology, IoT, Internet of Things with biotechnology. This is something that we just now, 3 of our students, I have a small, we said we'll enter into a competition on IoTs with a professor in ECE. Those students wanted to do something. So what we are now trying to design is that during, all of you are aware of what is known as sepsis? How many of you are aware of sepsis? Sepsis is something that when you get multi-organ failure, in the end stages of multi-organ failure, the bacteria just invade every thing of your every organ, and that leads to what is known as sepsis. What the bacteria do is that, so onset of sepsis can be treated, but once you reach 50%, patient will die. So how do you know the onset of sepsis? So one thing that we were thinking is, anyway, the person is in ICU, so he puts an oxygen mask. So when he has sepsis and the bacterial infection, can we drill a hole on that oxygen mask and then see what are all the gases that come out? Because bacteria give a lot of H2S. The body itself, as a last resort, starts giving H2S, carbon monoxide, all kinds of things. So can we now use both IoT and ICT to actually understand this process? Advanced analog devices actually give small things which are about $50 for looking at all the gases. So we are looking at it. Since we are in the semi-final, they may give us all these things free for us to actually do it. We have gone through 2 rounds, so another round we will try to do this. Yeah.
I had an opportunity to have a look at it as a demo, but I felt that the resolution was not so good, and even the image was slightly distorted.
Yeah.
Is there a possibility of improving on the quality of that?
Absolutely true. So this is exactly why we have to start understanding optics. So optics is magnification. So if your first lens magnifies it 10 times and your second lens magnifies it 10 times, it's a multiplicative factor. So the total image is magnified 100 times. So on the full scope itself, can you put another lens? So these are some of the things, or have a brighter, because the sun in the full scope, the sun is the thing. Of course, since it's a polydimethyl siloxane lens, you will see the aberration, optical aberration is very high. That is why you will see, luckily for us, contact lens is only small area, so we are escaping, but generally you will see that. So now you use a brighter source like an LED and then increase it. It's only another 5 rupees. So these kinds of things are some things that you can do in the college.
Can it be even extended as a fluorescent microscope?
And that's what we are trying. But now we see that fluorescence microscope, you also use the dye. And you have to peer inside. So again, as you said, it's only a 200 magnification. They say it's only 200. I mean, to look inside, we may need about 1,000. So can we put another lens? All these are some things that you can work out.